Phasors can make solving the differential equations governing steady-state sinusoidal responses a lot easier, but they also have another much larger benefit. They can make it unnecessary to even write the differential equation in the first place. In order to do this, though, we have to represent circuit elements in terms of impedances, which is the topic of this video. The first thing I want to do is reiterate what the problem is that we're trying to solve and the basic approach we're using to solve it. Always keep an eye on the big picture to keep from getting confused about the details. One detail that confuses people is complex arithmetic. Complex in this context doesn't mean complicated or involved. It simply means that the numbers used have both real and imaginary parts. In this unit, we're looking at the steady-state response of systems to sinusoidal inputs. That means that we're letting time go to infinity and only getting the particular solution to the differential equations. In this case, all of the signals in the system will be sinusoids with the same frequency, and we just need to determine the amplitude and phase angle of the various signals. Always make sure that the problem you're solving meets these criteria before you jump in and start using phasors and complex arithmetic. Under this set of conditions, the math becomes easier if we pretend that the input is a complex exponential rather than a sine or a cosine function. The complex exponential will have the same frequency, amplitude, and phase angle as the actual sinusoid being applied to the system. The real part of that complex function is then the actual physical signal that we're applying to the circuit. In sinusoidal steady-state analysis, the system response will also be a complex exponential with the same frequency as the input function, but with an unknown amplitude and phase angle. These values are represented by phasors, as we saw in the previous video. When we substitute the complex exponentials into the governing differential equation, the differential equations become algebraic and any time terms cancel out of the response. This only happens with linear differential equations, which is one reason why linear systems are so popular with engineers. When we solve the resulting algebraic equations, we're determining the form of the complex exponential response. The actual response will be the real part of this response. So the magnitude and phase of the calculated response will be the same as the magnitude and phase of the actual sinusoidal responses. Before we started using phasors, we'd been working in what's called the time domain. We were solving differential equations to find the response as a function of time. When we use phasors and complex exponentials in our differential equations, the time terms canceled out, and we were left with an algebraic equation that's not a function of time. The terms in the equation depend on frequency, and the equation is now said to be in the frequency domain. There's a huge advantage to frequency domain analysis beyond just writing a differential equation and converting it to an algebraic equation. We can actually convert the circuit schematic itself to the frequency domain and write the governing algebraic equations directly from the circuit, just as we did with purely resistive circuits. This eliminates the need for writing and solving differential equations entirely if we just need the circuit's steady-state sinusoidal response. In order to convert a circuit schematic directly to the frequency domain, we need to write the voltage current characteristics for the circuit components in the frequency domain. These IV relationships are called impedances. Impedances allow us to analyze circuits that contain capacitors and inductors in almost the same way we analyze purely resistive circuits in the first part of this course. First, let's determine the frequency domain voltage-current relationships for resistors. In the time domain, the voltage V sub r of t and I sub r of t are both functions of time. Ohm's law tells us that the voltage is equal to resistance times the current. If the voltage and current are both sinusoids and we're only interested in the steady-state response, those signals can be represented as complex exponentials whose magnitude and phase angles are in phasor form, VR underscore and IR underscore. We can substitute these relationships into the original time domain equation and get this result. As we'd expect, the e to the j omega t terms cancel out, leaving us with this expression. The governing equation for a resistor in the frequency domain looks exactly like Ohm's law. The voltage phasor is equal to the phasor current times resistance. This is a schematic representation of a resistor in the frequency domain. The resistor has a phasor, VR underscore, representing the voltage difference across the resistor, and a phasor IR underscore, representing the current through the resistor. The voltage phasor is equal to the resistance times the current phasor. As with the time domain version of Ohm's law, the frequency domain IV characteristic for a resistor is an algebraic expression. The phasor diagram showing a resistor's voltage and current looks like this. The resistor scales the magnitude of the current phasor according to the resistance. The length of the voltage phasor is equal to R times the length of the current phasor. If resistance is a real number, which it always is, there's no phase difference between the voltage and current phasors. A real number has zero phase angle, so the voltage and current phasors are shifted from one another by 0 degrees. The previous phasor results mean that the sinusoidal steady-state voltage and current for a resistor will look like this. The amplitudes of the voltage and the current are different. The voltage amplitude will be the resistance times the current amplitude. There's no phase shift between the signals, so there's no time shift between the sinusoids. The peaks and valleys of the signals line up in time. The fact that there's no phase shift between a resistor's voltage and current phasors is due to the fact that resistors don't store energy. Next, let's look at an inductor's frequency domain voltage-current relationships. In the time domain, the inductor voltage and current are functions of time. The voltage across an inductor is equal to the inductance times the derivative of the inductor current with respect to time. If we're looking for the inductor's sinusoidal steady-state response, we can represent the voltage and the current as complex exponentials in phasor form. The voltage phasor is V underscore L and the current phasor is I underscore L. If we substitute these relationships into this time domain differential equation, we get this. Notice that the derivative of e to the j omega t is j omega times e to the j omega t. As always, the e to the j omega t terms cancel out, and the voltage phasor, V underscore L, is equal to j omega L times the current phasor, I underscore L. We've replaced our differential equation, which is a function of time, with an algebraic relationship that's a function of the frequency omega. The time domain differential equation has become a frequency domain algebraic equation. This is a frequency domain representation of an inductor. The voltage across the inductor is V underscore L, and the current is a phasor I underscore L. The voltage phasor is equal to the current phasor times j omega L. Notice that we're still obeying the passive sign convention when we define our voltage and current phasors. The phasor diagram for an inductor looks like this. The magnitude of the voltage phasor is equal to the magnitude of the current phasor times omega L. The scaling factor is a function of frequency, so it depends on the frequency of the signal, omega, as well as the inductance. Multiplying by j also affects the phase between the voltage and the current. J in polar coordinates is 1 at an angle of 90 degrees. The j term doesn't affect the voltage magnitude, but it does add 90 degrees to the voltage phase. That means that the current lags the voltage by 90 degrees for an inductor. Or equivalently, the voltage leads the current by 90 degrees. Next, let's look at the effect of this relationship on the sinusoidal time domain voltages and currents. These are examples of what the sinusoidal waveforms for an inductor might look like as functions of time. The magnitude of the voltage is equal to omega L times the amplitude of the current. Current lags voltage by 90 degrees, so the current will always be delayed in time by a quarter of a period from the voltage waveform. The phase shift between voltage and current is because of the inductor energy storage, which causes the time domain voltage-current relation to be a differential equation. The differential equation, in turn, introduces the multiplicative factor of j in the phasor relationship, which results in the 90-degree phase shift. Our last circuit element is a capacitor. In the time domain, the capacitor voltage is V sub c of t and its current is I sub c of t. The capacitor current is equal to the capacitance times the derivative of voltage with respect to time. In the case of the steady state response to sinusoidal voltages and currents, we can use phasor notation and complex exponentials to represent the voltages and the currents. If we substitute these relationships into the time domain voltage current relationship, we get this. The e to the j omega t terms cancel out as usual. If I solve the equation for the capacitor voltage phasor, we get V sub c underscore is equal to 1 over j omega times c times I sub c underscore. Since 1 over j is equal to the negative of j, this is also equal to the negative of j over omega c times I sub c underscore. A capacitor's phasor voltage-current relationships can be expressed this way. The capacitor current is a phasor I underscore C, and its voltage is a phasor V underscore C. The voltage phasor is equal to the current phasor times 1 over j omega C, or equivalently, the negative of j over omega times C. The phasor diagram for a capacitor looks like this. The magnitude of the voltage phasor is 1 over omega c times the magnitude of the current phasor. As with inductors, the magnitude scaling is a function of omega, so changing the frequency changes this magnitude. This relationship is a function of frequency. The negative of j can be expressed in polar form as 1 at an angle of negative 90 degrees. So the voltage phasor lags the current phasor by 90 degrees. The functions of time that correspond to the capacitor voltages and currents might look like this. The amplitudes are different. The voltage phasor magnitude is equal to the current magnitude times 1 over omega c. The current leads the voltage by 90 degrees, regardless of the frequency. 90 degrees or 1/4 of a period, regardless of the frequency. The functions of time that correspond to the capacitor voltages and currents might look like this. The amplitudes are different. The voltage phasor magnitude is equal to the current magnitude times 1 over omega times c. The current leads the voltage by 90 degrees, or 1/4 of a period, regardless of the frequency. Equivalently, the voltage waveform is said to lag the current by 90 degrees. Our phasor voltage-current relationships can be used to define something called impedance. Impedance is represented as an uppercase Z, and it's defined as the ratio of a voltage phasor to a current phasor. This can be rearranged to define a voltage phasor as a current phasor times an impedance. Impedance defines the relationship between two phasors. In general, impedance is a complex number. However, impedance itself is not a phasor. It does not define the magnitude and phase of a sinusoid. It's a complex number that provides a relationship between phasors. The equations here are identical in form to Ohm's law. Ohm's law defines resistance as the ratio of voltage to current for a resistor. Impedance is defined as the ratio of voltage to current phasors for any passive circuit element. Because of impedance's similarity to resistance, the units of impedance are selected to be ohms. The symbol is the same as for resistors, an uppercase omega. Always keep the appropriate assumptions in mind. Using impedance implies that you're performing a steady-state sinusoidal analysis. Don't try to use impedances if the response you're calculating includes the natural response or if the input isn't sinusoidal. The phasor voltage-current relationships we've developed in this video for resistors, capacitors, and inductors can be represented as impedances. For resistors, the voltage phasor is the resistance times the current phasor. A resistor's impedance then is equal to its resistance. For an inductor, the voltage phasor is equal to j omega L times the current phasor. That means that an inductor's impedance is just equal to j omega times L. A capacitor voltage phasor is 1 over j omega c times its current phasor. A capacitor's impedance is then just 1 over j omega c, or equivalently, the negative of j over omega c. Now let's do a quick preview example to show how useful impedance can be in circuit analysis. This is the circuit we used in our previous example. Its input is a sinusoid, and we were looking for the steady-state voltage across the capacitor. If we convert the circuit into the frequency domain, We replace the voltages with phasors and the circuit elements with their impedances. The impedance of a resistor is just its resistance, and the impedance of a capacitor is negative J over omega C, which is negative J times 10,000 ohms. We can now treat this circuit exactly as if these elements were resistors. We have two impedances in series. We know the total voltage across that series combination, and we're looking for the voltage in one of the impedances. We can use a voltage divider. So the phasor Y is the total voltage, 3 at an angle of 20 degrees, times this impedance, minus J times 10 to the fourth, over the sum of these two impedances. Converting the denominator into polar form gives us this. Canceling these out, the phasor Y is 3 at an angle of 20 degrees times 1 over root 2 at an angle of minus 45 degrees, which is 3 over root 2 at an angle of minus 25 degrees. This is the same result we got before, we just got it a lot easier. This gives us the magnitude and the phase angle of the sinusoid representing the voltage across the capacitor. The wonderful thing about impedances is that if we represent the voltages and currents in a circuit as phasors and the circuit elements themselves by their impedances, we can analyze circuits that contain energy storage elements exactly the same way we analyze purely resistive circuits. This means that analysis techniques such as circuit reduction, voltage and current dividers, and so on apply directly in the frequency domain. I'll expand on this in the next video.